Take two. We're looking at page 14, problem number 2. This was your homework that was due today. You should have it in your packet. In this problem, they say to help in estimating the number of customers for an amusement park bungee jump, the operators hired a market research group to visit several similar parks that had bungee jumps. They recorded the number of customers on a weekend day. Since the parks charge different prices for their jumps, the collected data looked like this. We're talking about price, that's in dollars, and then the number of customers. When 15 customers came, when we charged $15, 25 customers came to the amusement park. Plotting that on a graph, which one should be the independent variable down here on the x-axis? Price per jump. Why?
Because it's independent, and it doesn't.
You're saying it's the independent because it's independent.
Yeah.
I need one more thing.
It doesn't matter on anything. It just is what it is. But like the dependent matters on the independent, so it doesn't matter on the.
I follow you.
number.
I think we can state it a little bit more concisely. There, that would be hard to write on a quiz. Amber.
Because the number of customers depends on the price per jump.
But why? That's what I'm trying to figure out. Why? Haley.
Because it can. Because if the price is low, you have more customers.
Yep. Like at Funtown, if they lowered the price, more people would go. Is that what you're saying?
Right.
That's exactly what we're trying to say. That's it. Does everybody get the difference between saying just, because that one depends on it, versus actually giving me a statement in the context of the problem? Context means with the story. And that's exactly what Haley did. Thank you very much. So this down here, this is going to be the price, leaving by process of elimination. This is the number of customers. And I'm just doing kind of a rough graph. Here in the packet, you had an opportunity to do it right on graph paper. If you didn't like to use the packet, you can just use graph paper. When we charged $15, we had 25 customers come. Let's go 5, 10, 15, 20, 25. So I'll put a dot right there because this in the table, 15 and 25, translates to a point on the graph that has an address that you can plot, 15, 25. And the next ones are, as the price per jump goes up by 5 each time, 15, 20, 25, 30.
It was 28. Yeah, it was
Good point. They go 28. Ooh, that's not a constant rate of change, is it? That can happen. 22, 18, 15. Next time I should get all the data up there before I press record. So we've talked about A. Now we're plotting the data on there. Yours should look like, if you plot these points accurately, it should look something like this. And even with my bad drawing there, they look like it's a pretty straight line. They look like they line right up. This one's different from the bungee jumper, though. In what significant way is this line, let me connect them here, is this line different from the other ones that we looked at? How about this? On the bungee jumper one, as the weight went up, the length of the cord went up. See how they're both going in the same direction? On this one, as the price of a ticket increases, what happens to the number of customers? Goes down. Thank you. Raise your hand so I can call on you like Amber was doing. There we go. See, those are different. The pattern of change is different. We're always going to look at the x-axis, the numbers going up. But here, on the y-axis, the numbers can do lots of things. We're talking about these go down at a constant rate of change. And since it's constant, I feel confident making some predictions over there, or in between the data points that I already have. And that's what this is good for, is making predictions. Does it make sense to connect the points? Why would you or wouldn't you? Amber.
Well, because it's not linear.
They look pretty linear to me. They might not be exactly linear, but I think they're pretty much linear. Something about points in real life, the data that you're going to collect in real life experiments, it's very rarely exactly on a line. But would you agree with me, Amber, that the overall trend of these points looks pretty straight?
Yeah.
In other words, if I talk about this point over here, I didn't measure anything out here. Would you expect it to be there or up there? The one that's down here, right? The one that's in line. Even though that these points, if you plot them precisely on graph paper, they don't come out to be exactly in a straight line, but they're pretty darn close, aren't they? Okay? I would agree. And thank you for agreeing to my leading question. Part D, we actually want to make some predictions on this. And then I'm going to talk about the equation, and then we're going to be done, so that this doesn't go on forever. Making predictions can be done with your table, with your graph, or with the equation that we don't get to till the last part. But we know that if I charge $20, this many people are going to come, and if I charge $25, this many people are going to come. We didn't do any measurements at a park that charged $23 per ticket. But if I charged $23 per ticket, that would be right in there somewhere, wouldn't it? Yeah. So how many people would you expect to come? How many customers do you think I'd have on the bungee jump if I charged $23? Caitlin?
So $23.20.
Looks about right to me. 23 is pretty much halfway between 20 and 25. And so 20 would be halfway in between 22 and 18. Right? Notice that as these numbers go up, these numbers are going down. So you gotta see the order that they're going in and recognize what the pattern of change is. You could do it on the graph by going over here and finding 23. Oh, let's say 23 is right here. I go up to the graph, and I look over here, and whatever that number is on the graph, that's how you use the graph to make the prediction. The last part is the equation. There were a couple other parts to this. If you have questions about them, if you don't get it, ask me, but I don't want to go over answers to things that you totally get. The next part is the equation. Let's look at the symbolic rule. They call it a symbolic rule. Calling it an equation or a function is also perfectly okay. N is the number of customers, and that, they say, is equal to 35 minus 0.07p. Nope, that's wrong. 0.7p, where p is the price per jump. What was the story of the problem again? Does anybody remember? I want you to keep in mind the context. Caitlin, what are we talking about here?
They charge on the weekend for the jump.
Exactly, and how many people will come to the bungee jump if they charge that price? So we're trying to come up with an idea of, I want some numbers. If I charge P dollars, how many N people are going to come? So with this, we can just plug in some numbers. And I'll tell you, if we plug in 20, that'll give me 35 minus 0.7 multiplied by 20. I just plugged in 20 where P was. What do you think I should get? Here's a hint. In this equation, what do you think I should get if I plug in 20? Amber Emery.
22?
Yeah. See, it's right there. We already measured that one. Okay? And with a calculator, and you should follow along on your calculators. By the way, if I type in this equation right here, 35 minus 0.7, and instead of typing P like up here, I type times 20. There we go. And I didn't get 22. Any ideas why not? It has to do with what I was talking to Amber a minute ago. Amber.
What?
Any ideas why this didn't come out to be 22? Who can take a guess? It has a lot to do with what I was talking to Amber about a minute ago. And it's a very important part of this. Do you remember Amber?
No.
I said that in real life, the points that you measure may not always line up exactly on a straight line.
A little bit off.
But it's darn close, isn't it? You know, it's hard to tell on Saturday the 14th whether or not we're going to have 21 people or 22 people come. There's no science behind this that'll tell you exactly that much, right, Sarah?
Yeah.
Okay? What it will tell you is a ballpark figure that you can predict, and you can use those predictions to run your business. So this is a real-world situation of how this might work. This is a 22. When we calculate it, it's a 21, but it's close. And if we calculated all of these, which we don't have to because they already gave them to us, we come up with close to these numbers. All right? Do you get the idea there? The big idea is that these numbers that they gathered in reality, this picture of the data that we drew, a graph, and this equation all represent the same things. There's multiple ways to represent the data, and any one of them is useful. Sometimes one is more useful than another in certain situations, but all of them can be used by you. Which one do you like best? Answer that question for yourself and make sure you're using that one when you do the quiz questions or test questions or you're doing any of these problems at home for homework. All right? Any questions on that? Then I guess we're done.